Do you believe that 124 light-years from Earth, there exists a planet called K2-18b? One that has captured attention through the first signals that begin to shake the way humanity searches for life in the universe. Orbiting a red dwarf star, K2-18, smaller and cooler than our Sun, at a distance just right to keep water on its surface from freezing solid or evaporating completely. But with a mass 8.6 times that of Earth, this is a super-Earth filled with paradoxes, a world where crushing pressure could destroy any familiar biological structure. With gravity about 30% stronger than Earth's, any life that exists here would have to endure extreme physical stress. Yet it is precisely this alien environment that opens an entirely different scenario from everything we have known about the possibility of life beyond Earth. Join us as we step into a deeper journey to uncover the mysteries of K2-18b and discover why this world is reshaping the way we define life. When modern space telescopes turned their gaze toward K2-18b, the shock did not come from seeing alien life, but from being forced to rethink how life itself can be observed. Through transmission spectroscopy, scientists confirmed the presence of carbon dioxide and methane in the planet's atmosphere, along with signals consistent with water vapor. This is not vague speculation, but peer-reviewed science results published in respected journals based on independent observations and detailed atmospheric modeling. K2-18b has a radius roughly 2.6 times that of Earth, an estimated mass 8 to 9 times greater, and orbits the red dwarf star K2-18b at a distance that allows surface or lower atmospheric temperatures to remain within the range where liquid water could exist. Its host star shines with only a few percent of the Sun's brightness. Yet because the planet orbits so closely, its year lasts just about 33 days. What truly matters is how science interprets these gases. On Earth, methane is often associated with biology anaerobic microbes, the digestive systems of animals, and oxygen-poor ecosystems all release methane. Yet methane is not exclusive to life. Carbon dioxide, likewise, is both a product of biological respiration and a common component of the atmospheres of lifeless worlds such as Venus or Mars. Water vapor signals the presence of water, but says nothing about whether that water participates in biology. What K2-18b's data actually reveal is an active atmosphere. It is not chemically simple, static, or easily predictable. The coexistence of methane and carbon dioxide under specific temperature conditions suggests a system that is continuously replenished or actively rebalanced. On Earth, Such an atmosphere would be difficult to maintain for long without ongoing biological processes disrupting thermodynamic equilibrium. This is precisely where the distinction between a biosignature and proof of life becomes critical. K2-18b offers biosignatures at a suggestive level, not definitive evidence. The true shock lies in the method itself. For the first time in history, humanity can analyze the atmospheric composition of a planet more than 124 light-years away, with enough precision to seriously discuss extraterrestrial biology. K2-18b's atmosphere, marked by high pressure, faint light from a red dwarf star, and a hydrogen-rich composition, may still sustain complex chemical cycles for billions of years. If life exists under such conditions, would it require oxygen, strong sunlight, or even a solid surface to take hold? It is from this point that the exploration must turn in a new direction. One where long-held assumptions about life itself are finally put to the test. When we look back at Earth's biological history, the assumption that life requires oxygen and sunlight begins to unravel. For nearly the first 2 billion years, Earth had almost no free oxygen in its atmosphere. Oxygen levels were millions of times lower than they are today. Yet life not only existed, it flourished. Anaerobic microorganisms dominated the planet for a span of time far longer than the entire history of humanity combined. Oxygen, which we now consider a fundamental requirement for life, was once a biological toxin that triggered one of the greatest extinction crises of the ancient world during the Great Oxidation Event around 2.4 billion years ago. If oxygen were used as the defining criterion in the search for life, most of Earth's own biological history would be overlooked. At the bottom of the oceans, where sunlight disappears after just a few hundred meters, fully developed ecosystems thrive at depths of 2,500 to more than 4,000 meters. Pressures here can exceed 400 bar. Temperatures hover near freezing. Yet beside hydrothermal vents, water can surpass 350 degrees Celsius without boiling due to the immense pressure. In this seemingly contradictory environment, life does not depend on photosynthesis. The foundation of the entire ecosystem is formed by chemosynthetic bacteria and archaea, drawing energy from reactions involving hydrogen sulfide, methane, hydrogen, and hot minerals rising from Earth's mantle. Fish, giant tube worms, mollusks, and many other complex organisms occupy only the upper layers of a living network that functions entirely without light. Sunlight, then, is not a mandatory condition. What truly matters is a stable energy source and the ability to sustain chemical reactions over long periods of time. On Earth, Geochemical evidence suggests that life may have emerged just 300 to 500 million years after the planet cooled enough for liquid water to exist. K2-18b orbits a red dwarf star, a class of stars that makes up roughly 70% of all stars in the Milky Way. Red dwarf light is dimmer than the sun's, rich in infrared radiation, and often accompanied by stellar flares. During early stages of stellar evolution, for years, these traits were considered hostile to life. But if life does not require intense light for photosynthesis, if it can exist beneath the surface or within deep oceans, then red dwarf stars are no longer adversaries. Instead, they may represent stable energy sources lasting tens to hundreds of billions of years, far longer than the sun's lifespan. If life emerges rapidly once conditions allow, as Earth's history suggests, then in a universe containing hundreds of billions of galaxies, each with hundreds of billions of planets, the implications are profound. Modern biology cannot yet provide a definitive answer, but studies of extremophiles from bacteria thriving in acidic lakes to organisms capable of withstanding ionizing radiation thousands of times stronger than what would kill humans demonstrate that life is not optimized for comfort but for survival. As scientists begin to accept the possibility that life can exist in environments utterly unlike our own, a new hypothesis takes shape. If a planet does not require an Earth-like surface, if it can be covered by a global ocean and wrapped in a hydrogen-rich atmosphere, then traditional biological limits are pushed far outward. From the question of life unlike us, scientific thinking is forced into a new landscape, one where deep ocean worlds, high pressures, and faint light become serious candidates for life. It is at this intersection that the Hycean world hypothesis emerges, opening the next chapter of the story, a type of planet where, if life exists, it would be entirely unlike anything Earth has ever known. As familiar criteria for Earth-like planets gradually reveal their limits, science is forced to expand its mental map. Not to search for a second Earth, but to accept a deeper truth. The universe has no obligation to replicate our environment. It is within this context that the Hycean world hypothesis emerged not as a declaration, but as a serious theoretical framework grounded in physics, chemistry, and verified exoplanet data. A Hycean world describes planets covered by global oceans and wrapped in thick, hydrogen-rich atmospheres, often orbiting red dwarf stars. In fact, planets with sizes between Earth and Neptune roughly 1.5 to 3 times Earth's radius and 5 to 10 times its mass are the most common type of planet in the galaxy. What is striking is that our own solar system contains no representative of this class. Hycean worlds may therefore represent a planetary norm that humanity has never experienced. According to atmospheric and planetary structure models, a Hycean world can retain light hydrogen thanks to sufficiently strong gravity, while still maintaining liquid water in the form of a deep ocean tens to hundreds of kilometers thick. A hydrogen-rich atmosphere creates an efficient greenhouse effect, stabilizing ocean temperatures at warm levels even when the planet receives less energy from its star than Earth does. In many scenarios, surface ocean temperatures are estimated to fall within a range of 0 to 100 degrees Celsius, suitable for complex chemistry to persist over long timescales. Light from red dwarf stars, the primary energy source for these worlds, is weaker than sunlight and concentrated largely in the infrared. This may leave the upper ocean relatively dark, but it also reduces temperature fluctuations and dramatically extends stellar lifespans. Red dwarf stars can exist for trillions of years, far exceeding the Sun's expected lifetime. This opens a startling possibility. Hycean worlds could sustain stable environments for prebiotic and biological chemistry far longer than any Earth-like planet. In such a setting, if life were to form, it would face little pressure to evolve rapidly or adapt to violent climate swings. It could evolve slowly, extremely slowly, within an environment that remains nearly unchanged for billions of years. And it is precisely this stability, not comfort, that may be the key ingredient for life. If life exists on a Hycean world, scientific models suggest it would most likely inhabit deep ocean layers rather than the surface regions where radiation from the host star is almost completely eliminated, pressure is high but stable, and temperature variation is minimal. Energy would not come from light, but from chemical reactions involving hydrogen, methane, ammonia, and minerals within the planet's mantle. These reactions could drive slow but continuous energy cycles, sufficient to sustain self-organizing chemical systems. At this level, life, if present, might exist only in microscopic forms, leaving no clear atmospheric signature. On a Hycean world with no continents, no fire, and no exposed metals, any intelligence that emerged would be forced down entirely different evolutionary paths. Rather than vision based on strong light, intelligent organisms might develop extraordinarily complex acoustic communication, similar to but far surpassing that of whales and dolphins on Earth. Sound travels more efficiently in water than in air, especially at low frequencies, enabling communication across vast distances. An ocean-based intelligence might hear its world in ways humans can scarcely imagine. Another possibility involves bioluminescence, a phenomenon already widespread in Earth's oceans. In a dark environment, networks of luminous organisms could encode information through rhythm, color, and intensity. On large scales, vast underwater light maps could function in ways analogous to written language or visual signaling in human societies. A more speculative, highly theoretical possibility is that intelligent life could exploit planetary magnetic or electric fields. Many Earth organisms already sense magnetic fields for navigation. On a Hycean world, where ocean currents and planetary structure might generate stable electromagnetic fields, intelligence could evolve to use and modulate these fields for communication or interaction with the environment. If such intelligence existed, the concept of technology would be entirely different. There would be no fire for metallurgy, no wheels for land-based infrastructure. Any structures might instead consist of pressure, adapted frameworks, vast biological scaffolds anchored in the deep ocean, or luminous networks stretching hundreds of kilometers existing not as cities, but as something closer to a collective nervous system. These ideas are strongly influenced by science fiction, and it must be stated clearly, there is currently no scientific evidence to support them. To date, no data indicate that intelligent life exists on K2-18b or on any Hycean world. The Hycean hypothesis, therefore, is not merely a theory about planets. It is a test of how humanity understands itself. And if life elsewhere exists, in forms that never produce signals we know how to recognize, then is the silence of the universe truly evidence of loneliness? The Hycean hypothesis forces science to confront its own limits. We cannot send probes, drill into alien oceans, or meet any form of life. All we have is light and faint chemical traces. If life exists there, whether microscopic or intelligent, how would we recognize it from hundreds of light years away? If life truly exists on K2-18b, more than 124 light-years away, every familiar notion of exploration collapses. There would be no probes, no landing robots, no samples returned to laboratories. If life exists there, it will not be discovered through direct contact. It can only be inferred through light, mathematics, and universal physical laws. When K2-18b passes in front of its host star, a small fraction of starlight is absorbed by the planet's atmosphere. Each molecule absorbs light at specific wavelengths, creating dark lines in the observed spectrum. By analyzing these lines, scientists can determine the chemical composition of the atmosphere, a technique known as transmission spectroscopy. This method is not new, but for the first time in history, the sensitivity of current generation telescopes has pushed it to a level where serious discussion of extraterrestrial biology is possible. However, in a closed system without a continuous energy source, chemical reactions tend toward equilibrium, a state in which significant change ceases. When this principle is applied to exoplanets, science must proceed with far greater caution. Geochemical processes, volcanic activity, radiation from the host star, or even asteroid impacts can also produce unusual atmospheric configurations. K2-18b places us at the threshold of a new scientific era, one in which knowledge is no longer built from direct observation, but from extraordinarily subtle indirect traces. It forces biology to expand its definition of life, philosophy to reconsider humanity's place, and society to confront a foundational truth. Earth is no longer the sole reference point for life in the universe. The greatest shock will not come from technology, but from meaning itself, from what scientific data may ultimately reveal about our existence. From a scientific perspective, confirming life beyond Earth, even in the form of simple microorganisms, would be the greatest revolution in biology since Darwin published the theory of evolution. For the first time, biology would no longer be the science of a single planet. Life would no longer be studied as a phenomenon tied exclusively to Earth's unique geological history, but as a process that can arise under different physical conditions. This would force biology to expand its definition of life, moving beyond DNA, liquid water, and familiar chemistry toward more universal principles. The ability to sustain itself, exchange energy, and evolve over time. Astronomy and planetary science would be transformed just as fundamentally. For decades, exoplanets have been classified mainly by mass, radius, and orbital parameters. If life were confirmed on a world like K2-18b, those criteria would no longer be sufficient. Planets would be evaluated not by how closely they resemble Earth, but by their ability to maintain stable biochemical systems over long timescales. Yet the deepest impact would likely occur not in laboratories, but in human consciousness. If life were confirmed in another star system, a long-held belief would collapse. Earth would no longer be seen as the only oasis, but as one example within a far larger set. The existence of bacteria, or simple organisms on K2-18b, would say nothing about civilizations, consciousness, or technology. But that is precisely what makes the shock more profound. It reveals that life does not need to rise to intelligence to possess cosmic significance. If life is not exclusive to Earth, then protecting life, including life on our own planet, takes on a broader meaning. It raises questions about humanity's responsibility toward the world we inhabit, and toward exploring other worlds without destroying ecosystems we do not yet understand. At the cultural and social level, the impact would not be uniform. Some would see the discovery as a confirmation of humility, humanity as a small part of a vast universe. Others might feel unsettled, even threatened, as the idea of human centrality begins to erode. If life were confirmed on K2-18b, the universe would become biologically more crowded, yet emotionally lonelier for humanity. Distances measured in hundreds of light years, combined with the physical limits imposed by the speed of light, mean that other life, however real, would remain beyond direct contact. In this context, the true value of the discovery lies in how it reshapes our understanding of life itself. It affirms that life is a phenomenon that can emerge whenever physical laws allow. And if that is true, then the human story is no longer the story of an exception, but the story of a rare branch of awareness within a living universe. The discovery of life on K2-18b would not be merely an astronomical finding. It would be a historic turning point, shaking the deepest pillars of human understanding. A planet covered by vast oceans and wrapped in a complex atmosphere of water vapor, methane, and carbon dioxide sends a powerful message. The conditions that give rise to life are not a privilege unique to Earth. These chemical signatures represent the first empirical hints that the universe is not silent or lifeless as we once imagined, but may be alive with processes unfolding in forms humanity has never conceived. Yet K2-18b is also a lesson in humility and scientific discipline. It reminds us that the path to understanding the universe must be built on verified evidence and precise measurement, not on assumptions shaped by human expectation. If the hypotheses surrounding K2-18b are confirmed, the very concept of life will have to be rewritten. Earth would no longer stand as a solitary oasis in a vast cosmic darkness, but as part of a far larger and more intricate web of existence. we would be forced to accept a new reality, that on distant worlds, utterly different in structure, pressure, and environment, life can still emerge and evolve in silence. Such a discovery would not only bring an end to the era of cosmic solitude, but also open a new chapter in humanity's journey, a chapter in which we begin to learn how to understand, and perhaps one day communicate with, a universe filled with unnamed neighbors. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.